A very good morning, good afternoon, good evening to all my friends, participants and students for this NPTEL MOOC course, the title of which is Application of Forecasting, Regression and Time Series Models. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, as you are all aware that there are three main focus areas or subject topics for this course. The first being forecasting, second is regression and third is time series models. And we are almost at the fag end of regression models and we will cover few more important and interesting concepts in regression models. This is week number 9 and lecture number 42. So, what is the coverage for this lecture? Coverage would be the following points. We will consider the balance loss function, which we did discuss very briefly, and when we consider the balance loss function, we will consider that balance loss being made up of two important other loss functions. One being the ordinary least square, which we have discussed, which we have found their best estimate for beta, for which we have found out y hat. We will also consider the other loss function along with squared error loss being the LINEX loss function. We have discussed how the LINEX loss looks, we have discussed its properties, the applications of LINEX loss. We have also considered how the estimate can be found out for theta, and as you take different combinations of theta considering L values, you can find out the beta also under LINEX loss. And furthermore, we have also considered the y hat value under LINEX loss. Now, when I am using the word considered, it means that I have given the formula and also solved the problems and shown the numeric values in details and compared them. If you remember in the 40th and the 41st lecture. We will continue more such discussion in the 42nd lecture. The other coverage, depending on how we proceed, because if there are detailed discussion which I think needs to be done, I will do that. The other part, as I was saying, is simply checking how the other loss functions look and how they can be utilized in the case of estimation and prediction. Now, continuing the discussion from where we left at the 41st class is that consider that theta is the parameter. When I am talking theta is the parameter, I am using the word parameter in a very general sense. So, theta can be either beta or considering beta naught, beta 1, beta 2 for the multiple linear regression. And then as you remember in the 41st class, I mentioned that in the balance loss function you are trying to balance, make a judicious choice, and the choice was about goodness of fit and precision of estimation. When I am talking about the concept of precision of estimation, it is to do with trying to find out the beta values. And goodness of fit is in the subsequent stage, once you have found out beta, you will utilize that beta values in order to find out y hat that would be considered as the goodness of fit. So, theta is the word I am using very generally, considering whether you want to find out the parameters, whether beta or y. Now, if theta is the parameter, then obviously there is a corresponding estimate which is theta hat. Now, the question when I am using or the statement which I am using is estimate, it would mean under which context. And if you remember, we were discussing that the risk, which is the estimated loss, depending on whether the environment is LINEX and the estimate is used LINEX. That is one case. Another case being environment being LINEX and the estimated being ordinary least square estimate, you will find, and very simply I have only stated the result, that under the conditions, few conditions, I have only given the result, that the risk for the case when the environment in both the cases is LINEX, but if the estimate used is LINEX rather than ordinary square, then for the case when the estimate used is LINEX, the risk is always lower than the case when the estimate is ordinary least square or SEL. And I have also given a very qualitative feel that you are suffering from fever, then obviously a medicine which alleviates or is able to help you recuperate fever would be more effective than the one medicine which is more effective or more is more of for the stomach upset. So, depending on the environment, you will try to utilize the estimate, and this, after stating the result, I have also given the values and shown that using graphical methods how the overall risk would basically behave for both these cases. So, I will continue that discussion further on, considering the balance loss, where the combinations will be much more, and you will get a very nice picture, very clear cut picture how the balance loss function would be utilized, depending on whether you want to give more weightage or less weightage to the precision of estimation, or more weightage, less weightage to the goodness of it. If I denote as usual, the delta value is the difference between the parameter and the estimate, then obviously the loss function would be a function of this delta, which is the difference between theta and theta hat. So, the balance loss function has two parts. Part 1 is the goodness of fit, which I am marking in blue, and the other part which I am marking in red is actually the precision estimation. So, the precision estimation has to do with the first stage, goodness of fit has to do the subsequent stage, and you give weightages here. The weightages which you give is I am using the symbol here as lambda, and this lambda values are between 0 and 1, almost like the case, if you remember, for the forecasting we had used the weightages as alpha 1, alpha 2, alpha 3, but always ensuring and seeing that the sum of the weights are equal to 1, and also the weights are between 0 and 1, both inclusive. So, in this case, the value of delta lambda would be considered as the weightages lambda and 1 minus lambda. So, this I should mark with blue. My apologies, I will basically remove the coloring. So, this 1 minus lambda is the weightages for the precision of estimation, and when you have lambda, this is for the goodness of it, and lambda can be 0. Similarly, 1 minus lambda would be 1, or lambda would be 1, 1 minus lambda would be 0. So, you will basically weight it, balance it, that is why the concept of balance loss function. Now, where would we use it, and that will come very soon. Now, there are lot of end result formulas given. Do not be bothered about the proofs, they are not required. Only what is required is to check the formula and utilize it. Now, the question would be, if you want to utilize it, have they been shown in the PPT slides? Yes. They have also been solved very simply in the Excel sheet. I will come back to the Excel sheet within few minutes as we proceed. Now, what we are doing, and let me tell you the background before we proceed. So, we are giving here 4 consecutive models, that is model 1, 2, 3, 4, and they are used for both finding out beta and then subsequently you can find out the value of y also. But I have kept my concentration and analysis on trying to find out the values of beta or else theta, because theta is a multiplication of L into beta. So, once you find out theta, you can find out beta values, and then once the beta values are found out, you can go to the next stage, which is the goodness of it, and find out the values of y. That is a very simple step, the later part. Now, what we want to do is, we will pan out the storyline as follows. In model 1, and these important points I will keep repeating for each model. In model 1, the squared error loss portrays the precision of estimation, which is related to concept of the beta theta values, and LINEX loss is used to find out the goodness of it, and we are already incorporating that in the model and then proceeding. Hence, you will find it accordingly. Now, when I am trying to find out the goodness of it or the precision estimation, the words of precision and goodness would be interchanged, in the sense that in some cases it will more concentration is given on y, or in some other case more concentration is given on finding out theta or beta, whichever the case is. The first model says that I am going to utilize the case where you have the balance loss function I want to find out with respect to beta and beta hat. The first part, which is squared error loss, is given for the case where I want to find out the square of the difference of the predicted value and the actual value, y, which is of n cross 1 column vector, and y hat is also n cross 1 column vector. Y hat are the predicted values. Square of that is actually the squared error loss. That is why squared error loss is the precision of estimation. And when I come to the fact of finding out the LINEX loss, it is utilized for the case of goodness of it, which is related to the value of theta or beta, and here it is. I use the violet color. And obviously, the first component squared error is multiplied by lambda, and second part, which is goodness of it, is multiplied by 1 minus lambda, the weights. So, the storyline again, lambda multiplied by squared error loss corresponding to the difference squares of the y and y hat, and 1 minus lambda is the weight which is being multiplied with the LINEX loss, and LINEX loss is mainly focusing on trying to find out the loss corresponding to the theta or beta values. So, once you have that, what is now the second stage? The second stage is, in this the environment is a combination of squared error and LINEX, but now what is the estimate we are using? The estimate we will use for model 1 is squared error, only squared error, not LINEX. Again I am repeating, the environment is a combination of squared error and LINEX, but the estimate we will be utilizing is only the squared error estimate for beta. That is why it is given as beta suffix squared error, which the formula we all know and which I am underlining with the red. So, once I put it, there are some few statistical steps. Again I said it is not required for this course. Once I find out the risk, which is expected value of the loss, and if you remember I mentioned that why expected value of the loss is to be found, because as you keep changing the sample, the beta hat values will change. As the beta hat value changes, hence obviously y hat value will also change. So, if I, and we also know the distribution of beta hat, normal with certain mean and certain variance, which I have repeatedly said that and stated that along with the proof, very simple proof, because that was important I thought in the slides, in the previous set of slides, when we are doing simple multiple linear regression. So, when I find out the expected value of the loss, it comes out to be the risk, and this is pertaining to the risk for model 1, and it is given here. What are the important facts? Lambda value, which we consider as the weightages, is where it is green tick mark, it is known, the value is given from the data or from your assumption. Lambda would be known between 0 and 1. N is the sample size, we know. P is the number of independent variables, we know. Sigma square is the the variance corresponding to the error, that epsilon is with normal with 0 mean, and in the simplest case as 1 as variance or sigma square as the variance. And we also considered, sorry I am repeating it, that sigma square for each error remains constant. The concept of multicollinearity, or to be more precise, heteroscedasticity, homoscedasticity, which will hold, then autocorrelation, non-autocorrelation, which will hold. And I have shown that and explained that time and again, and that is important. Then 1 minus lambda is known, A or A square, which is the parameter utilized in the LINEX. So, LINEX laws had two parameters, A and B. One was scale, one was shape. A is the shape parameter. Sigma square known, L is the vector, whether row or column will depend how you quantify it, and that only consists of 1 for the simplest case. And if you remember in the last two class, I have shown different examples and different scenarios where you consider L as only one element being 1, such that you are able to find out all the values of beta. That is a very nice way of trying to find out the beta values. Given theta, we know X transpose from the data, we know X inverse can be found out, L values are known. So, in this formula everything is known. Now, the important thing is this, and I am only mentioning for model 1, then subsequently repeat it for model 2, 3 and 4. So, the first part on the right hand side of the equality, which I will circle in orange, is a scalar. N minus p is a scalar, sigma square is a scalar, lambda is a scalar. So, this is scalar. So, if I want to find out the risk, so obviously the question would be, is the second part on the right hand side after the plus sign, is it also scalar? So, let us check. 1 minus lambda is a scalar, here a square sigma square by 2, everything is scalar. Now, let us check here this part. I will write the size of this matrix and column and row vector. So, it will become easy for all of us to understand. So, if you consider X, I will use a different color. So, it is visible. If I use X, it has got a size of n cross k, X transpose has a size of k cross n, then L transpose has a size of 1 cross k, and L has a size of k cross 1. So, if I consider all the things, k cross n into n cross k is k cross k, 1 cross k into k cross k is 1 cross k, 1 cross k into k cross k is 1 cross 1, which is a scalar. That means, you find out the second part of the risk is also scalar. So, you will add up two scalar quantities and get the risk for model 1. When I come to model 2, here also you are using the balance loss function, again two components, squared error loss, precision of estimation, LINEX loss, A quote portrays goodness of fit, and if I consider the concept of goodness of fit, which is I use green color, this is the goodness of fit component because it is a LINEX loss component. And when I come to the precision of estimation, it is basically estimation of the part corresponding to beta. While goodness of fit is for theta, because once you know beta, then only you can find out theta, and then subsequently y values can be found out. So, main concern is that you are utilizing the precision of estimation for beta and in subsequently giving the weightages of 1 minus lambda to the loss corresponding to the goodness of fit, which is for theta subsequently, beta then theta. And in this model 2, again you have the environment, squared error, LINEX, as you can see in this slide, squared error corresponding to precision of estimation, LINEX corresponding to the environment of goodness of fit. So, it is a combination of the environment. So, the environment has both squared error and LINEX loss coming and playing their part. Now, if lambda is 50%, 0.5, then the overall, the so called emphasis coming from the squared error loss is 50%, LINEX loss is 50%. If lambda is 0, in this case the squared error is taken out, only the environment is LINEX. If lambda is 1, then the corresponding LINEX loss is taken out, the environment is only squared error. Now, with this concept, let us proceed to the next slide. Here again we are using the estimate, not the environment. The estimate again is considered at the squared error loss, and I am marking with the color red. So, this is the estimate. So, in model 1 also environment was combination, estimate was the squared error loss. In model 2 also the environment is a combination, combination means squared error and LINEX, and the estimate is LINEX, squared error. Now, you may be saying, asking the question that if the environment is same qualitative wise as squared error and LINEX, what is the difference? Difference, if you check the slides, one was with corresponding to y and theta, another was corresponding to, next case was corresponding to beta and theta. So, there is a subtle difference in that. So, if I use that, let us check the risk, and here I will again clarify the fact what is the corresponding size of this right hand side dimension wise of the risk. If I consider the second part, I will come to directly to the second part first. So, I will put a tick mark, 1 minus lambda is scalar, a square, sigma square, all these are scalar, and we know this part is also scalar. So, this right hand side after plus are all scalars, and minus 1 is a scalar, so it is not a factor. Now, if I come to the first component, this is not a scalar. Reason being that if you have that, the fact of lambda sigma square and this part, which is, if you remember, I had taken the size as you have the size of k cross n and n cross k, and inverse of that is still a k cross k. So, how would you consider that? Depending on the model, so the overall risk would be considered. I would not go into the details for that, but it can be utilized, and for some other type of problems it can be utilized. That is not, again I am saying that is not an part and parcel of this course, this is more into the area of sampling. So, you can find out model 2 risk also. For model 3, again we are considering Squared error is corresponding to precision of estimation, and which would be corresponding to square of y minus y hat. So, if somebody has to be very precise, that person would say that why not use it as a goodness of fit. You can do that, but I want to explain the concept, that is why I am using those words. And this squared error component is multiplied by lambda, while the fact if I go to the LINEX component which portrays the goodness of fit, for which I will use the blue color. So, that corresponding to 1 minus lambda is the weightages, and goodness of fit is more related to the theta, because whether you want to find out theta or beta, even though beta would be found out then theta, but it would not matter, because if you remember, theta is a scalar which is a multiplication of two vectors, either column and row, such that it should be compatible. So, L and beta both are vectors, and they are corresponding to the fact column and row. Based on that, you find out beta, which is, as I said, is a scalar. So, once I have the background, again a combination of environment being squared error and LINEX, and as lambda is 0, the environment is totally LINEX, and if 1 minus lambda is 0, which is lambda is 1, the environment is totally squared error. Now, in this case, there is now a change. The change is environment remains a combination as for model 1 and 2, combination of squared error and LINEX, model 2 same, model 3 also same. But in model 1 and 2, if you remember, I am repeating it, the estimate was squared error estimate. But now we are using the LINEX loss estimate for theta LINEX. And if you remember, theta LINEX, the formula is given from the book. So, based on that, once you have it, utilize it. So, now let us double check. This component about the dimension, this component part, we all know green with circled is always a scalar. So, a sigma square by 2 scalar. So, after minus is a scalar. And again, if I check here, this one I will use say violet color. So, the dimension, so x transpose x is basically k cross k, L1 would be 1 cross k, L transpose, x transpose you know is k cross n, y you know is n cross 1. So, if you have, so this part is k cross n, 1 into k cross n is 1 into n, 1 into n into n into 1 is 1 into 1. So, it is also a scalar. So, the estimate theta LINEX is a scalar, because theta has to be a scalar. So, once you put that in this formula, you have two parts. Part 1, which I am now circling with blue, light blue, this is a scalar, lambda, n is known, lambda is known, p is known, sigma square is known. Sigma square is the error of the variance of the error. And in the second part, A is known from the LINEX, n minus p you know, sigma you know, again square is basically you are squaring it, 1 minus lambda known, again this whole part is known. So, model 3 this is also a scalar, and we have now model 4. But considering that the class timing is over, but I thought I will discuss this model 4 in the next class, and then compare the results of 1 and 3, 2 and 4 I would not, and I will come to the reason why. And if you remember, I had mentioned all these things are solved very simply in the Excel sheet. With this, I will end this class and continue more discussion further on. Thank you very much and have a nice day.